They see it as well. So you did a titration curve from your lab just now, and notice these are polyprotic acids. Poly is the prefix for more than one. Protic meaning donates an H+. Here is one of these polyprotic acids. Here is a second one. Hopefully you notice that these curves look different than yours that you just did from the lab. The one that you did for the lab has one steep incline. This has two. This has three. This first acid, when I look at question number 1, what is the difference between the two acids shown for the titration above? This first acid, since it has two steep inclines, we would call this a diprotic acid. Di meaning two, protic donates two. Which means this curve on the right-hand side would be what type of acid? Triprotic acid. So there's our difference between the two. Question number 2. Again, I could care less what the acid is. So if we know it's diprotic, we're just going to call it H2A because it has two hydrogens that it can donate. And again, I'm referring to the graph on the left right now. Sodium hydroxide, very common to titrate with. So that is our red liquid, I guess, in the burette. The H2A is a weird acid. It is a green acid. What we're going to do is, if it was titrated with NaOH, write down the products at the first equivalence point. Notice the graph. The first equivalence point is where the first steep incline occurs. It also mentions that sodium is a spectator ion, so we don't need to include that in our answer. So if I were to write that reaction, here's my H2A, my acid I started off with. I'm adding hydroxide to it. That would leave me, well, water is a product in all these neutralizations. Then it also leaves me with HA minus. So if you just had to write the products, it would be the 2 on the right-hand side. It just was easier for me to write the entire equation. So again, at that first equivalence point, right here, H2A and HA minus are what's present. Can someone figure out question number 3 then? What would be present at the second equivalence point? Adam?
A2 minus and
Yeah. The A2 minus or minus 2, however you want to call it, plus H2O. Because after the second equivalency point, we get rid of all the remaining hydrogen ions that could be donated. Again, when we write H2A, those hydrogens do not get donated or react at the same time. That's why we have Ka1, Ka2, different equilibrium constants for acids. If you look at your graph then, for question number 4, notice the first equivalence point is at a pH of 6. Why is it at a pH of 6?
because there's still going to be H plus and the HA minus after the first equation.
After that first reaction, if we look back at question 2, there's still HA minus remaining. That's an acid. It has a hydrogen to donate. And if it donates that acid, it can make more H plus ion, just like Braden said. So our answer to number 4 is after the first equivalence point, there's still acid remaining. It's now the monoprotic HA minus. And if there's acid remaining, the pH should be below 7. Number 5, if you look on that graph on the left-hand side, the second equivalency point is at a pH of 12. This one's a little bit trickier. Why is it at a pH of 12? I think the first question, number 4, was a little bit easier. Hey, there's HA present. That HA minus is still an acid. That's why it's below 7. This pH is above 7 by a fair amount. Andrew?
Well, because the A2 minus doesn't have any protons to donate, and then you titrated it with base.
It has to deal with the A2 minus. Now, once we get where the graph starts to flatten out,
to take a proton from water and create hydroxide.
A2 minus is the conjugate base of that acid. We started off class with that whole aluminum sulfate conjugate base type stuff. So this, now I'm doing double arrow this time, can react with the water, that hydrolysis process, to make HA minus and some hydroxide. Just like last class, when you did a reading guide to show that when you titrate a weak acid with a strong base, the equivalency point is above 7. It's not because, well, the base was stronger than the acid, so there you go. The reason why is when you have a strong base, like sodium hydroxide is in this example, with a weak acid, which the HA minus I would consider a weak acid, the conjugate of that weak acid undergoes hydrolysis. It reacts with water to create this hydroxide shown right here. You're going to see that in the lab next time. Now, you guys are going to have monoprotic acids next time, or not a monoprotic base, but a base that only has one hydroxide in it. So you're not going to have the multiple steep inclines like these graphs do. But your equivalency point is not going to be at 7 like it was today, because of that conjugate of either the weak acid or the weak base, depending upon what you have next class. Finally, on this side, number 6 says both graphs label the midpoints. Which is half the volume of the titrant to reach each equivalence point? The graph on the right, so we're looking at the other graph right now, shows an equality of H3A minus equals H2A, H3A equals H2A minus at the first midpoint. Explain why this is the case for a titration of H3A after adding 5 mils of OH. So, if I write down for that number 6, that first expression, H3A plus OH minus makes H2A plus water, similar to what we did above. If that graph shows it takes 10 mils for this reaction to be complete, 10 mils of OH minus, but instead I only add 5 mils, that means after adding 5 mils, I have equal amounts of this and this, because half of the H3A has reacted, the other half hasn't reacted. Again, this is an important point when we look at graphs. The half equivalency point, or the half equivalence point, is when each step of that titration, we've used up half the acid. And if you look at question number 7, it indicates the importance of this then. It says the midpoint of a titration curve is important because the pH at the midpoint is equal to the pKa. Shows you the Henderson-Hasselbalch equation. Because if our A minus and our HA concentrations are the same, which is in this case on the problem I have on the board, halfway through, H2A minus is the same concentration as H3A. 1 over 1, the log of 1 is 0. pH equals pKa. This is something that is brought up year after year on the college board. They always like to ask you questions dealing with the titration curve. Titration curve is good for 2 reasons. So if I flip back up to the top here, if I know that this is a diprotic acid, that second equivalence point, I know that volume then. I can use that volume when I'm doing my solution stoichiometry or my M1V1 equals M2V2. I can solve for the concentration of the unknown. But the second thing that we can get out of these titration curves is that equivalence point, that midpoint, as it were, labeled on this one right here. Because that value then can help us solve for the pKa and the Ka. And that's what question 7a is going to ask to start off with. If we look at the graph on the right-hand side, I don't know why my graph is kind of cut off right now. But right here, 7a says, what's the approximate pKa2 for the acid shown on the graph on the right? Give me a whole number.
5.
5. We like that? Let's write down 5 for question 7a. Remember, pKa equals the negative log of Ka. In question B, it asks, what's the Ka? Well, the inverse function of this is Ka equals 10 to the negative pKa. And if our answer to 7a was 5, what's the Ka then? 10 to the negative 5th. So 1 times 10 to the negative 5th would be our Ka value. Using the half equivalency point, you can look at the graph and then determine what is the pKa. It's the same as the pH. That's due to pH equals pKa, Henderson-Hasselbalch equation. Then we can solve for the Ka. Last couple of questions. C says for polyprotic acids, what's true between the relationship between Ka1 and Ka2?
Ka1 is much larger.
Yeah, Ka1 is always bigger. It's always easier to lose the first hydrogen than it is the second. For example, sulfuric acid, H2SO4, the first loss of hydrogen is completely strong. It doesn't even have a K value for sulfuric acid for the first loss of hydrogen because it's strong. But HSO4 minus does have a K value. The second loss of hydrogen doesn't happen as readily. Finally, number 8 says it is sometimes noted that at the midpoint of a titration, a solution that has been created is an ideal buffer. What do we need for the composition of an ideal buffer? Acid
and its conjugate base.
Acid and its conjugate base in equal molar amounts. So halfway through that midpoint is when that occurs. That's why we can use that equation for number 7 to do what we just did as well.